So this video covers section 4-3 on what your book calls the addition rule, which goes from page 39 to page 42 in your note-taking guide. So we have already talked about this term mutually exclusive, but we want to come back to it. Remember, we said for two events to be complementary, they had to be both mutually exclusive and exhaustive. So we've talked about this briefly before, but this word mutually exclusive, or your book will sometimes call this disjoint. So two events are mutually exclusive or disjoint, or you can think of this as separate if they can't happen at the same time. Okay, so let's see if we drew a diagram right here, and this is event A, we'll call it, and this is event B. All right, so you see right here, these two guys overlap. All right, so this would not be mutually exclusive. So if two events are mutually exclusive, they can't happen at the same time, or they are completely separate. So that would look more like this. A is over here and B is over here, and these two events are mutually exclusive because there is no overlap. So they can't happen at the same time, or they are completely separate. So if two events are mutually exclusive, so I'm on this case over here on the right where we're completely separate, what's the probability of A happening and B happening? These can't happen at the same time because they are completely separate. Well, that would be impossible. So we represent that with a probability of 0. So if two events are mutually exclusive, the probability that A or B occurs. So this symbol that we have here is the union symbol, which means OR. So we've already looked in section 4-4 at the AND symbol. The OR symbol is a union, which looks like a U. So if I know I'm separate, well, this is going to be the probability of my first event plus the probability of my second event. So let's look at an example of this. Suppose you roll a traditional die numbered 1 to 6 once. Let event E be that you roll an even number, and let event F be that you roll a 5. So I'm going to denote this E. I'm going to write out my sample space. So if I roll an even, well, I could get a 2, a 4, or a 6. Now I'm going to let event F be that I roll a 5. Well, there's only one option there, it's a 5. So now, are these two mutually exclusive? Could it happen that I roll an even and a 5 at the same time? Well, if I'm rolling one die, no, these are completely separate. Let's see if we can draw our Venn diagram. This might help a bit. So here is our even, and in here we have 2, 4, and 6. Here is event F, and the only number in here is a 5. And then I have 1 and 3 out here, which are in neither of these groups. Are these two mutually exclusive? Yes. They can't happen at the same time. Or you can think of these two groups are separate. There's no overlap. So now, if we want to know what's the probability that we roll an even or a 5, so I'm going to denote this probability of an even. My symbol for OR was that union symbol of 5. Well, because I know that these are mutually exclusive, that's going to be the probability that I roll an even plus the probability that I roll a 5. So an even, half of the numbers on a die are even, so that would be a half. Or you can think of it as 3 out of 6, 2, 4, and 6. Plus the probability that I roll a 5, well, there was only one 5 on a die with 6 sides. So if I'm going to add these guys up, I might want to get a common denominator first. 3/6 plus 1/6, which is 4/6 or 2/3. So suppose 15 students in your class own a TI calculator, 10 students own a Casio, 5 own neither, yet no student owns more than one calculator. What is the probability that a randomly selected student has a TI? Okay, well, the first thing I need to do is figure out how many students are in this class. So I'm going to draw my Venn diagram here. Now, this first piece right here, yet no student owns more than one calculator. Well, I know that these two groups do not overlap. So I'm going to have my TI folks over here. Then I'm going to have my Casio folks over here. So I have 15 here. I have 10 here, and then I have 5 folks out here that didn't purchase either. Here we have a total of 30 students. So the probability that a student has a TI calculator, well, that's going to be 15 out of 30, which is a half. So what's the probability that a randomly selected student owns a Casio? So I'm going to use a C to represent that event. So the probability of a Casio, well, there are 10 of those folks out of 30, which is a third. So what is the probability that a student owns both a TI and a Casio? Well, we need to look at this little point over here underlined in green. No student owns both. So the probability of a TI and a Casio, well, that's 0. Then what is the probability that a randomly selected student owns a TI or a Casio? Well, this is going to be represented with this union symbol. And I can just add those two probabilities that I've already found. So we get the probability that a student owns either a TI or a Casio is 5/6. So in example 3, we're considering a traffic light that is red for 35 seconds, green for 35 seconds, and yellow for 5 seconds. What is the probability that you make it through the light when it is yellow or green? So again, here we see an or. So I want to ask myself, are these two events mutually exclusive? So is it possible for a traffic light to be both yellow and green at the same time? Well, nope, those are completely disjoint. So the probability that I'm yellow or green is going to be the probability that I'm yellow plus the probability that I'm green. So the probability that we pass through this intersection when it is yellow, well, it's yellow for 5 seconds out of a total of 75 seconds. Plus, well, when is it green? It's green for 35 seconds out of 75 seconds. So this would be 40 out of 75 seconds, which would reduce to 8/15. So next we want to look at the possibility when two events are not mutually exclusive. So in this case, there could be some sort of overlap between the two. So if we're not mutually exclusive, well, we would take the probability of A, as we did before, plus the probability of B. But if these guys overlap, we might have double counted here, so we're going to have to subtract off the probability of A and B. be. So I think this is best illustrated with an example. So here I'm coming back to this contingency table we looked at in the last section for grades by gender. And I'm going to start off by filling out this contingency table with my totals here. So we're interested in the probability that a randomly selected student is either male or earned a C. So we are male up here. And students earned a C right here. So clearly these overlap. So these are not mutually exclusive, because do you see there are some students that are both male and earned a C? These 5 students right here. So if I wanted to find the probability that I'm male or I earned a C, well, that's going to be the probability that we select a male plus the probability that a student makes a C, but I need to subtract off the probability that we're a male and we earned a C, because we don't want to count those men twice. So the probability that we're male, that we select a male, well, there were 15 males out of 60. All right, the probability that a student earns a C, well, 20 students earned a C out of 60. But you see here, I counted these 5 students in both of those groups. So I need to subtract off the students that I double counted, which would be 5 out of 60. So this would give me a total of 30 out of 60, which would be a probability of 1/2. Another way that you might do this problem is to look at your contingency table and just add up every cell where I'm either a male or earn a C, and just make sure not to count these males who earn a C twice. So in example 5, you're interested in the amount of money students spend to take a statistics class. So you poll your class and learn that 20 students purchased the textbook, 15 students purchased a calculator, 10 students purchased both a book and a calculator, and 5 students did not purchase either. So I'm going to come over here and see if we can fill in this Venn diagram. So I have my book over here, my calculator over here. So we had 10 students right here that purchased both. Now if we had a total of 15 students that purchased a calculator, and 10 of them are right here, we have 5 students over here. Next, we had 20 students that purchased the book. Well, we've already counted 10 of those, so we have 10 more students out here. And lastly, we have 5 students that purchased neither. So if we wanted to find the probability that a student either purchased the book or the calculator, that's going to be the probability that a student purchased the book plus the probability that they purchased the calculator minus the probability that they purchased both. So the probability that a student purchased the book, we had 20 students purchase the book out of 30 students. The probability that they purchased the calculator, well, we had 15 students purchase a calculator out of 30. But now I want to subtract off the students that purchased both, because I don't want to count those twice. So this would end up being 25 out of 30, which is 5/6. Now another way that you might do this is once you've drawn your Venn diagram here, I think it's more apparent that you can look straight from this Venn diagram and see, well, where am I either the book or the calculator? Well, that's anywhere inside here. That would be 10, 10, and 5, which is 25 out of 30. So I think when you draw your Venn diagram, it helps you a good bit. Of the 30 students in your class, 20 ate breakfast in the dining hall, and 25 ate lunch in the dining hall. 15 ate both breakfast and lunch in the dining hall. What is the probability that a randomly selected student ate either breakfast or lunch in the dining hall? Okay, so I'm going to fill out this contingency table to help me here. So I know that there's a total of 30 students. So 20 ate breakfast. Well, if I had 20 eating breakfast, then I know that I had 10 that did not. 25 ate lunch, so I had 5 that did not. And now I know 15 ate both lunch and breakfast. So which of these cells would represent breakfast and lunch? That would be a yes for breakfast and a yes for lunch, so I would have 15 folks here. So now once I get this far, I can fill out the rest of my table. Well, I know then that there were 5 here that ate breakfast but not lunch. I can see that there are 10 here that ate lunch but not breakfast. What could I put in this cell to get these to add up? Well, that would just be a 0. So now I want to know, what's the probability that a student ate breakfast or lunch? Well, that's going to be the probability of breakfast plus the probability of lunch, and then I want to subtract off the probability of breakfast and lunch. Breakfast, we had 20 out of 30. Lunch, we had 25 out of 30. And then I want to subtract off those that ate both, which is 15 out of 30. So this would give me 30 out of 30, which is 100%, or 1. Now another way that you might do this problem from the contingency table, well, where am I either breakfast or lunch? Well, that would be here and here. So if I added these up, I would get 30 out of 30, which is 1. You just need to make sure not to count these folks that ate breakfast and lunch twice. Next, I want to know, what's the probability that a student ate neither breakfast nor lunch in the dining hall? So I ate no breakfast and no lunch. Well, that would be this cell right here. So the probability that I did not eat breakfast, and I hope you remember my notation there, and I did not eat lunch, well, that's going to be 0 out of 30, which is 0. So I want to come back to these dice that we looked at when we started this unit. And we've already looked at this problem once, but I want to take another perspective and see if we can use our addition rule here. In this problem, you roll both die C and die D at the same time. You're interested in the probability that C rolls a larger value than D, and you know that C will win if C gets a 6 or D gets a 1. So we want to find the probability that C rolls a 6 or that D rolls a 1. So my options for C, I could have a 2, 2, 2, 2, a 6, or a 6. Then my options for D, I could have a 1, 1, 1, 5, 5, and 5. So I want to know when either C rolls a 6 or D rolls a 1. Well, one way we could do this, if you already have your sample space written out here, well, let's just go through, is either C a 6 or D a 1 here? Well, yep, D is a 1. So it's here, 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 and so forth. Now here, when C is a 2 and D is a 5, that's a no. So if we wanted to use our fraction representation, C is a sixth 1/3 of the time. So if I break this into thirds, this is when C is a 6. Now, if I break this in half, this top half is when D is a 1. But do you see that these two overlap here when I get both? The easiest way to do this, I could just count when is C a 6 or D a 1. Well, I could count all the check marks I had here and make sure not to double count these guys, and I get that that would be 24 out of 36, which is 2/3. If you wanted to use our formula, well, this would be the probability that C is a 6 plus the probability that D is a 1, but I need to subtract off that overlap, which is when C is a 6 and D is a 1. So this would be 1/3 plus 1/2, but then I need to subtract off this overlap here, which hopefully you can see that this overlap, if I break this into 6 pieces, this overlap is going to be 1/6. So this would be 2/6 plus 3/6 minus 1/6, which is 4/6 or 2/3. So clearly, if you have your sample space drawn out here, the easiest way to do this would just be to check off where either of them is satisfied and make sure not to double count. So in example 8, we want to know what's the probability that a randomly selected person is either male or has a birthday this month. So we're going to use the letter M to represent male and B to be that we have a birthday this month. So I want to know what's the probability that we're male or we have a birthday this month. Well, that's going to be the probability that we select a male plus the probability that someone has a birthday this month, and then we need to subtract off the overlap, which is that we're male and we have a birthday this month. So the probability that a randomly selected person is a male, well, we have 2 genders, so that would be a half. The probability that their birthday is this month, well, there's 12 possible birthday months, and this month would be one of those, so that would be 1 out of 12. But then we need to subtract off the overlap, because perhaps one of these participants in this experiment is both a male and has a birthday. So to find an and here, we would multiply. So here this would be 12 out of 24 plus 2 out of 24, and then I want to subtract off the overlap, which is 1 out of 24. So this would be 13 out of 24. So next we're going to say, well, what's the probability that a randomly selected student has a birthday this month or next month? Well, the first question I want to ask is, does this overlap? Well, I don't think it's possible to have a birthday both this month and next month. So these are mutually exclusive. So this goes back to what we started with. In this case, we can just add the two. So that would be 1 out of 12 for this month plus 1 out of 12 for next month, which would give us 2 out of 12 or 1/6. So this second example, example 9, is much easier because our 2 events do not overlap. So lastly, we have this standard deck of 52 cards, and I have our sample space right here, and we want to know what is the probability that we either select a heart or an ace. So I'm going to pull one card at random. So we're going to do this first with our formula, and then we'll draw out the sample space and see if we can make sense of this. So I'm going to use H to represent heart and A to represent that we get an ace. So the probability that we get a heart or an ace, well, that's going to be the probability of a heart plus the probability of an ace, but then we need to subtract off the overlap, which would be the ace of hearts, because that would fit in both categories. So the probability that we get a heart, well, there are 4 suits, so that would be one of the 4, which is a fourth, and plus the probability of an ace, well, there are 13 denominations, and the ace is one of those 13. And then I need to subtract off the overlap, that I am a heart and an ace. Well, there is only one card in the deck that is both a heart and an ace, so that would be 1 out of 52. So this would be 16 out of 52, which would reduce, I think, by 4, so this would give us 4 out of 13. So if we wanted to use our sample space here, 1/4 of the time we're a heart, so that would happen here. 1/13 of the time I am an ace. But we need to subtract off the overlap, which happened right here with the ace of hearts, because we don't want to count that one twice. Or if we have our sample space written out, we can just count in how many boxes was I either a heart or an ace. Well, that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 out of my 52 options.